Look closely at this vertical cliff face in Chongqing, where gravity seems to have lost its absolute power. A massive 1,200-ton prestressed concrete beam hangs suspended 90 degrees above a jagged canyon floor. It sits merely 0.7 meters away from the residential balconies of a 15-story apartment complex. This is not an optical illusion, but a brutal masterclass in extreme structural and mechanical engineering. How do engineers secure thousands of tons of transit track onto porous limestone mountain walls permanently? The system must withstand massive dynamic loads and torsional forces every single time a monorail train passes. A single mistake in calculating the stress distribution could trigger a catastrophic chain reaction geological collapse. To solve this, the architectural matrix abandons all traditional flat-surface city planning methods completely. They have created a continuous multi-layered transportation artery operating across 5 distinct spatial dimensions simultaneously. Watch how the monorail glides smoothly along the cliffside, defying the sheer drops right beneath it. There are no massive ground pillars here. The entire track behaves like a flexible mechanical ribbon. It is held tightly to the rock face by a matrix of deep underground anchor blocks. This integration relies heavily on high-intensity shock-absorbing hydraulic modules distributed along the alignment. These components dissipate the intense kinetic energy generated by an 80 km/h train effortlessly. Because of the dikes and steep geometry, traditional logistics and concrete pouring methods were useless. Bringing prefabricated girder blocks up these steep, unstable mountain tracks was mathematically impossible. Therefore, engineers had to redesign the entire field manufacturing sequence from scratch. They converted the sheer cliff edge into a fully functional micro-manufacturing assembly line. A specialized heavy-duty cantilever slipform machine was deployed directly onto the track head. This massive robotic printer moves forward incrementally along a precise computer-guided path. It continuously pours ultra-high-performance concrete over a dense network of prestressed steel tendons. Look at the high-intensity automated welding systems fusing heavy titanium alloy structures effortlessly. Automated arms move with absolute mechanical precision, casting sparks across the cold gray metal. This advanced concrete mix contains high-tensile diamond core fibers for maximum structural durability. It provides 5 times the tensile and compressive strength of conventional civil concrete structures. Each structural segment is pushed out into empty air according to a rigorous balancing sequence. Internal tensioning cables instantly adjust to absorb the growing, shifting load of the cantilever structure. The weight of the extending beam must be perfectly counterbalanced at the root anchor points. Let us examine the internal matrix of this massive rock face via specialized technical diagnostics. To prevent the cantilever beam from overturning, deep underground high-strength anchor tendons are required. Each deep rock anchor consists of dozens of high-strength steel tendons bundled together tightly. These tendon groups are drilled 40 meters straight into the most stable geological layers. A specialized polymer grout is injected under extreme pressure to eliminate any internal air pockets. The grout solidifies rapidly, creating a permanent mechanical bond within the mountain core structure. High-capacity hydraulic jacks then stress each tendon bundle with hundreds of tons of force. This immense tension clamps the heavy steel load-bearing plates firmly against the rock face. This complex structural anchoring process requires an absolute mechanical tolerance of under 0.1 millimeters. If the drilling angle deviates by even 1 single degree, the entire stress distribution fails. Unbalanced stress paths would cause severe structural fractures when the dynamic rail loads arrive.
The sheer scale of this cliffside development is staggering. Engineers are facing immense geological challenges, yet progress remains on schedule.
The mountain bedrock itself is converted into a colossal foundation, absorbing all kinetic energy. Once anchored, the construction sequence advances to the most delicate phase, cantilever segment joining. 2 independent mechanical arms advance from opposite sides of the cliff toward each other. The remaining gap between these massive overhanging structures narrows down to just a few centimeters. Cold mountain winds buffet the open construction zone as the setting sun hits the steel. Field engineers monitor real-time data feeds closely inside a temporary cliffside command outpost. High-precision satellite positioning arrays track the minute physical movements of both structural segments. Both massive cantilever blocks are slowly aligned using advanced micro-differential hydraulic jack systems. The alignment process must compensate for unexpected thermal expansion caused by shifting ambient temperatures. If structural contraction occurs before locking the joints, the entire stress balance shatters. When the final heavy hydraulic lock engages, a continuous, unified mechanical ribbon is established. This massive concrete and steel artery now hugs the mountain curves flawlessly without ground pillars. Now, the technical sequence shifts from structural closure to internal reinforcement and vibration mitigation. Engineers begin installing specialized heavy-duty elastomer dampening pads along the concrete track bed. These mechanical isolation layers absorb high-frequency kinetic energy from moving trains completely. Without these dampening matrices, continuous operational vibrations would slowly pulverize the limestone base. Let us analyze the mechanical properties of these advanced anti-vibration shock modules closely. Each custom damper module consists of multi-layered, vulcanized rubber bonded directly to titanium plates. They redirect extreme lateral kinetic forces down into the deep rock anchor tendon matrix. Next, high-tensile steel rail guides are laid over the dampening pads with absolute precision. Automated rail fastening machines follow immediately behind, locking the high-tensile steel guides down permanently. They apply precise torque to massive, heavy-duty structural anchoring bolts along the path. Every single bolt connection undergoes strict digital torque calibration to ensure uniform load distribution. Next, field personnel begin executing the highly critical aluminothermic rail welding procedure at joints. Industrial workers wear high-visibility safety vests, hard hats, goggles, and heavy-duty work boots. They focus entirely on preparing the specialized refractory molds around the raw rail gap. A chemical mixture of iron oxide and aluminum powder is ignited inside a crucible. The intense chemical reaction rapidly generates molten steel exceeding temperatures of 2,000 degrees. This molten alloy pours smoothly into the mold, fusing the rail ends into one piece. The intense heat radiates across the cold metal surfaces, creating brilliant sparks in darkness. Once cooled, specialized automatic hydraulic shearing machines cut away the excess metal slag cleanly. Heavy mechanical grinders follow, polishing the welded seam down to a mirror-smooth finish. This seamless rail design completely eliminates traditional joint gaps, minimizing dynamic operational vibration. Without joint gaps, train wheels glide over the cliffside tracks with minimal acoustic impact. With the structural guideway completed, the technical sequence advances to power grid installation. Heavy tensioning units slowly string massive copper conductor lines through insulated overhead bracket fixtures. These specialized electrical conduits provide continuous power supply directly to the monorail system. Every single power junction box is fully sealed against moisture and extreme mountain fog. Automated diagnostic units run complete circuit isolation tests across the newly established grid.
As you can see behind me, the scale of the operation is truly unprecedented. Engineers are working tirelessly to secure the cliff face before...
The electrical grid operates with extreme stability under heavy load conditions without failures. Now, the engineering process transitions to the comprehensive quality control and safety testing phase. Specialized laser scanning arrays are mounted on the track to measure surface flatness. Digital sensors record multiple geometric parameters across the entire length of the concrete structure. The telemetry data flows instantly into the central engineering system for extensive structural validation. Next, engineers prepare the heavy physical stress testing sequence using multi-axle ballast cars. These heavily loaded test vehicles simulate extreme structural stresses far exceeding standard operational weights. The vehicles are slowly driven onto the overhanging cantilever sections under strict supervision. High-sensitivity strain gauges monitor microscopic concrete deflection variations down to the micrometer level. The structural D.M. responds within expected limits, demonstrating massive elastic capability under pressure. Following successful static structural loading, automated stress testing equipment simulates repetitive dynamic vibration frequencies perfectly. The technical validation process ensures long-term fatigue resistance under continuous decades of rapid transit operations. Specialized ground-penetrating radar arrays scan the raw limestone bedrock around anchor plates again. This secondary scan ensures absolutely zero microfractures developed during the heavy structural stress testing phase. The concrete track structures are officially certified safe, meeting every extreme national engineering benchmark. Now, The sequence moves directly into the comprehensive integration of advanced automated signaling systems. Field personnel begin installing high-precision optical fiber data links along the main alignment track. These specialized communication arrays transmit real-time telemetry from moving trains back to command centers. Every single signaling module undergoes thorough electronic validation to eliminate any potential data latency. Next, the heavy mechanical cantilever slipform equipment is dismantled and removed from the site. Large industrial platform units are slowly lowered back down to the canyon floor via hydraulics. The temporary cliffside scaffolding matrix is stripped away cleanly, revealing the complete bare concrete infrastructure. This massive concrete ribbon now cuts through the rocky mountain terrain with absolute architectural grace. The structural pathway stands ready to receive the first official test monorail train vehicle. In the central operations facility, technicians initiate the full system activation sequence silently. Main power breakers engage with a heavy clunk, flooding the entire overhead grid with high-voltage electricity instantly. From the dark mountain tunnel, the sleek silver test monorail train emerges slowly onto the open track. The train wheels glide smoothly over continuous welded rail joints, creating a soft mechanical hum. The vehicle accelerates gradually, tracking perfectly along the tight curves of the vertical limestone cliff face. Inside the moving cab, advanced diagnostic displays show absolutely zero lateral deviation or structural shifting. The deep rock anchor tendon matrix absorbs every ounce of dynamic operational vibration effortlessly. Advanced elastomer dampening pads completely isolate the raw mountain bedrock from high-frequency kinetic energy. The first complete transit test run across the impossible vertical alignment is executed with absolute defect. This massive concrete ribbon stands as a monument to modern high-precision engineering and structural integration. The system successfully connects previously isolated urban sectors across the complex multidimensional geography of Chongqing. It redefines every standard of mass public transportation infrastructure within impossible vertical topographies worldwide. The Cliffside Railway operates day and night, a flawless machine moving thousands of commuters safely.
We are live from the precipice of the ambitious coastal development, where Phase 1 is already exceeding expectations. The scale of the operation is truly unprecedented.
We do not destroy the mountain. We become a permanent part of its ancient structural matrix. Subscribe to Dark Machine Universe to analyze more extreme mechanical processes and mega projects with me.